Okay, hi everyone, welcome back to this video series on data centers routing protocols. IP routing is essentially the process of moving packets from one network to another network via routers. To be able to forward packets, routers need an accurate map of their internetworks to refer to called a routing table. Routing tables can be created manually, a process known as static routing, but going with this method is a lot of work, especially if you're dealing with a decent sized network. The much easier alternative is dynamic routing, which uses protocols to find networks and update routing tables. But in networking, as in life, there is no free lunch, and dynamic routing will cost you in bandwidth on your network links as well as in CPU processing. Routing protocols define the set of rules used by a router when it communicates routing information between neighboring routers. The first dynamic routing protocol I'm going to cover is Routing Information Protocol, or RIP, versions 1 and 2. RIP is only used in small networks now. Enhanced Interior Gateway Routing Protocol, EIGRP, is a Cisco protocol that predictably runs on Cisco routers and is very important because it's one of the two most popular routing protocols in use today. We'll explore some of the features of EIGRP, and then I'll describe how it works and demonstrate how to configure it with the Nexus operating system, the NX OS. After that, you'll be introduced to the open shortest path first, OSPF routing protocol. OSPF is the most popular routing protocol in use today, especially in data center environments. First, I'll define some vital OSPF terms and then move on by showing you how the protocols work internally. I'll wrap up the chapter by detailing OSPF's advantages over RIP, and finally you'll learn how to configure OSPF on the NX OS. Dynamic routing. Even though I'm going to show you how to configure static routes on Nexus, dynamic routing will be the focus in this chapter, and we're already going to zero in on routing protocols within the NX OS environment. We'll start with RIP and then move on to EIGRP and OSPF, but you need to know that there are two types of routing protocols used in internetworks: Interior Gateway Protocol, IGPs, and Exterior Gateway Protocols, EGPs. IGPs are used to exchange routing information between routers within the same autonomous system, or AS. An AS is a collection of networks under a common administrative domain in which all routers sharing the same routing table information are included. EGPs, like Border Gateway Protocol, enable communication between autonomous systems, but that's beyond the scope of this book, so I won't be covering it here. Routing protocols basically drive dynamic routing, so I'm going to give you some fundamental information about them next. We'll start with the discussion about administrative distances and the three different kinds of routing protocols. Routing protocol basics. The first and most foundational concept you need to be familiar with is that of administrative distance, referred to as the AD, which is used to rate just how trustworthy the routing information from a neighboring router actually is. Administrative distances. An AD is actually an integer ranging from 0 to 255, where 0 is the most trusted and 255 is the least. A value of 255 means no traffic will be passed via this route at all. If a router receives two updates listing the same remote network, the router will simply check the AD and add the route with the lowest value into the routing table. Sounds simple, but some times both advertised routes to the same network have the same AD. When that happens, the routing protocol metrics like hop count and the line's bandwidth come into play to choose the best path to the remote network. The advertised route with the lowest metric will be placed in the routing table, but if both advertised routes have the same AD as well as the same metrics, then the routing protocol will load balance to the remote network by sending packets down each distance link. Table 10.1 lists the default administrative distances that a Cisco router uses to decide which route to take to a remote network. Route source default AD, connected interface 1 static route 1 EIGRP 90 OSPF 110, RIP 120, external EIGRP 170, unknown 255. This route will never be used. Always remember that when a network is directly connected, the router will always use the interface connected to that network. Also, if you configure a static route, the router will then believe the route over any other learned routes no matter what. You can change the administrative distances, the administrative distance of static routes, but by default they have an AD of 1. What this means is that if we change the AD of a static route to a higher number, we can then configure routing protocols without having to remove the static routes, which is good because they'll be used as backup routes in case the routing protocol experiences some type of failure. These are typically referred to as floating static routes, so understand that if you have a static route and a RIP advertised route and an EIGRP advertised route all listed in the same network, by default the router will always use the static route unless you change the static route's AD to a value greater than 1. Routing protocols. There are 3 classes of routing protocols. Distance vector. The distance vector protocol is in use today. Use distance to determine the best path to a remote network. RIP's strategy for doing this is to keep track of each time a packet goes through a router, known as a hop. The route with the least number of hops to the network will be chosen as the best one. The vector part of the name simply indicates direction to the remote network. RIP is a very popular distance vector routing protocols and periodically sends the entire routing table to directly connected neighbors. Link state in environments using link state protocols, also called shortest path first protocols. The routers existing in them each create 3 separate tables. A table to keep track of directly attached neighbors, a table for referencing the topology of the entire internetwork, a table to be used as the routing table. As you can see, link state routers definitely accrue a lot more information and therefore know more about the internetwork than routers using a distance vector routing protocol ever will. Routers running link state protocols like OSPF send updates containing the status or state of their own links to all other directly connected routers on the network. This information is then propagated to each of their neighbors. Hybrid protocols like EIGRP use aspects of both distance vector and link state. Cisco typically refers to EIGRP as advanced distance vector or just distance vector, but in the past they have referred to as EIGRP as a hybrid. There just isn't a set rule for choosing and configuring routing protocols. You really have to do it on a case-by-case basis, so having a working knowledge of exactly how the different protocols work will enable you to make solid network design decisions that will fully meet the individual needs of any client and or business. Now it's time to go deeper into specifications of each of these routing protocols, beginning with a closer examination of the distance vector class. Distance vector routing protocols. The distance vector routing protocol algorithm works by making routers pass their entire routing table's contents onto the neighboring routers. The neighbor routers then incorporate the routing table entries they've received into their own routing tables. This is called routing by rumor because a router that receives an update from a neighbor router totally believes the information about remote networks without confirming it. As mentioned, it's entirely possible for a network to have multiple links to the same remote network. In this scenario, the administrative distance of each update that a router receives is checked first, and if it's the same, the protocol will then rely on metrics to determine the best path. RIP simply uses hop count to decide the best path to a network. If it finds more than one link with the same hop count on the same network, it'll automatically opt to load balance. RIP can perform round-robin load balancing for up to 16 equal cost links, but only 8 by default. Routing Information Protocol. Routing Information Protocol, RIP, is a true distance vector routing protocol. It sends the complete routing table out to all active interfaces every 30 seconds and uses only hop count to determine the best way to a remote network. RIP has a maximum allowable hop count of 15 by default, meaning that 16 is viewed as unreachable. RIP works well in small networks, but it's really inefficient on large networks with lots of routers or those with slow WAN links. RIP version 1 uses only classful routing, which means that all devices in the network must use the same subnet mask. This is because RIP version 1 doesn't send updates that include the subnet mask information. RIP version 2 adds a feature called prefix routing that includes the subnet mask information along with route updates. This is called classless routing. RIP version 2. RIP version 2 is mostly the same as RIP version 1. They're both distance vector protocols, which means that each router running them will send its complete routing table out to all active interfaces at periodic time intervals. Also, the timers and loop avoidance schemes such as hold down timers and split horizon rules are the same in both RIP versions. Both RIP v2 and both RIP v1 and RIP v2 are configured using classful addressing, but as I said, RIP v2 is considered classless because subnet information is included with each route update. Both versions have the same AD of 120. There are some key differences that make RIP v2 more scalable than RIP v1, but I definitely don't recommend using either RIP version in your network. RIP's big virtue is that it is an open standard and you can use it with any flavor router as just described in the sidebar. Should anyone really use RIP in a modern internetwork? And remember that RIP is still an exam objective. It's just that OSPF is worlds better, and it also happens to be open standard. RIP requires way too much bandwidth, making it terribly inefficient to use in the vast majority of today's networks. Why go there when you have other more elegant options available? Table 10.2 delimitates the differences between RIP v1 and RIP v2. RIP v1, RIP v2. Distance vector, maximum hop count 15, maximum hop count 15. classful, classless, broadcast based, uses multicast 244.0.0.9, no support for VLSM, supports VLSM networks, no authentication, allows for MD5 authentication, no support for discontiguous networks, supports discontiguous networks. RIPv2, unlike RIPv1, is a classless routing protocol, meaning that it includes subnet information with route updates even though it is configured as classful like RIPv1. This is an important distinction because by sending the subnet mask information with the updates, RIPv2 can support variable length subnet masks, VLSMs, as well as summarization of network boundaries. By the way, this can and does cause more harm than good in our present day network designs. All key difference is that RIPv2 can support discontiguous networks if you disable auto summarization feature. EIGRP features in operation. Enhanced EIGRP is a classless enhanced distance vector protocol that uses the concept of an autonomous system, or AS, to describe the set of contiguous routers that run the same routing protocol and share routing information. EIGRP is classless, so it includes the subnet mask in its route updates. And as you know now, the ability to advertise subnet information allows us the freedom to use variable length subnet masks, VLSMs, and manual summarization when designing our networks. People sometimes refer to EIGRP as a hybrid routing protocol, but Cisco typically refers to EIGRP as advanced distance vector. It has characteristics of both distance vector and link state protocols. For example, EIGRP doesn't send link state packets as OSPF does. Instead, it sends traditional distance vector updates containing information about networks plus the cost of reaching them from the perspective of the advertising router. But EIGRP synchronizes topology tables between neighbors at startup and then sends specific updates only when topology changes occur, which is a definite link state characteristic. This flexibility makes EIGRP suitable for huge networks. It has a maximum hop count of 255 with the default set to 100, but please don't get confused by what I just said. EIGRP does not stop hop count as a metric as RIP does. In EIGRP speak, hop count refers to how many routers an EIGRP route update packet can pass through before it will be discarded. This effectively limits the size of the AS, but has absolutely no bearing whatsoever on how metrics are calculated. There are a number of powerful features that make EIGRP a real standout from other protocols. The main ones listed support for IP, IPv6, and some other useless router protocols via protocol dependent modules considered classless, same as RIPv2 and OSPF. Support for VLSM, CIDR, support for summaries and discontiguous networks, efficient neighbor discovery, communication via reliable transport protocol RTP, best path selection via diffusing update algorithm, dual neighbor discovery. Before EIGRP routers are willing to exchange routes with each other, they must become neighbors. There are 3 conditions that must be met for neighboring establishment. Hellos received, AS numbers match identical metrics, K values. Link state protocols tend to use hello messages to establish neighborhoodship, also called adjacency, because they normally do not send out periodic route updates, and there has to be some mechanism to help neighbors realize when a new peer has moved in or an old one has left and gone down. To maintain the neighborship relationship, EIGRP routers must also continue receiving hellos from their neighbors. EIGRP routers that belong to different autonomous systems, ASES, don't automatically share routing information, and they don't become neighbors. This behavior can be a real benefit when used in larger networks to reduce the amount of route information propagated through a specific AS. The only catch is that you might have to take care of redistribution between the different ASES manually. The only time EIGRP advertise its complete information is when it discovers a new neighbor and forms an adjacency with it through exchange of hello packets. When this happens, both neighbors advertise all their information to one another. After each has learned its neighbor routes, only changes to the routing table and propagates from then on. When EIGRP routes receive their neighbors' updates, they store them in a local topology table. This table contains all known routes from all known neighbors and serves as the raw material from which the best routes are selected and placed into the routing table. Let's define some of the terms before we move on. Feasible distance, FD. This is the best metric among all paths to a remote network, including the metric to the neighbor that is advertising that remote network. The route with the lowest FD is the route that you will find in the routing table because it is considered the best path. The metric of a feasible distance is the metric reported by the neighbor, called reported or advertised distance, plus the metric to the neighbor reporting the route, reported advertised distance, AD. This is the metric of a remote network as reported by a neighbor. It is also the routing table metric of the neighbor and is the same as the second number in parentheses as displayed in the topology table, the first number being the feasible neighbor. Neighbor table. Each router keeps state information about adjacent neighbors. When a newly discovered neighbor is learned, the address, the interface of the neighbor are recorded, and this information is held in the neighbor table stored in RAM. There is one neighbor table for each protocol dependent module. Sequence numbers are used to match acknowledgements with updates packets. The last sequence number received from the neighbor is recorded so that out of order packets are detected. Topology table. The topology table is populated by the protocol dependent modules and acted upon by the diffusing update algorithm Joule. It contains all destinations advertised by neighboring routers, holding each destination address and a list of neighbors that have advertised the destination. For each neighbor, the advertised metric distance, which comes only from the neighbor's routing table, is recorded as well as the FD. If the neighbor is advertising the destination, it must be using the route to forward packets. A feasible successor. A feasible successor is a path whose advertised distance is less than the feasible distance of the current successor, and it is considered a backup route. EIGRP will keep up to 16 feasible successors in the topology table. Only the one with the best metric, the successor, is copied and placed in the routing table. This to the show IP EIGRP topology command will display all the EIGRP feasible successor routes known to a router successor. A successor route, think successful, is the best route to a remote network. A successor route is used by EIGRP to forward traffic to a destination and is stored in the routing table. It is backed up by a feasible successor route that is stored in the topology table if one is available. By using the successor and having feasible successors in the topology table as backup links, the network can converge instantly, and updates to any neighbour make up only the traffic sent from EIGRP. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.